Okay, so let's begin. What are the first points? So one point which Carrie pointed out to me that I should have mentioned, and I think it is important, is to note that base affine space depends on the group, not just on the root system. So for example, it's a nice exercise that we've been discussing at lunches to understand the base affine space for SL2 and PGL2 and see that you get really different spaces. And another way of, probably one way of motivating base affine space, and we talked about the Chevalier multiplication, is just, this is the geometric object that you can see from applying Tanakian formalism to your group, in some sense. Okay, so out of your group, you can produce, in a very natural way, a graded ring, or a multi-graded ring. And this ring is functions on the base affine space. And also the other question that I asked last time, which Carrie responded to, was the question about the why are they called the Drinfeld-Plücker relations. And I found it helpful. There's a section, I think maybe section 4 in Frenkel-Gates-Vilonen, where this is explained briefly but usefully. And I've added that to the notes. And that's the last point, that now we're jumping around a bit more. It's important to have good notes, and luckily there are really excellent notes being produced by Anna. And if you haven't looked at those, I would encourage you to do so. She's doing a really excellent job with the notes. So they're currently at about 240 pages, and I guess we should stop when they get to 300 pages. Okay, so now we're back on the constructible side. So let me say, so basically this will be, this lecture is about constructible sheaves. On finite flag varieties. And Bray groups. So when I started preparing these notes, I optimistically hoped that we'd have an hour on this and then we'd do an hour on the affine case. And of course, this was optimistic. So this will be the whole lecture today. And then next week, we'll do the case of constructible sheaves on affine flag varieties and affine Bray groups. And just to motivate where we're going, we wanted to construct this functor from free, G check, and tilde to Pi. So this is I equivariant perverse sheaves on the flag variety, on the affine flag variety. And somehow a key tool is the so-called Wakimoto sheaves. And there's a lot of not too difficult and beautiful maths around understanding Wakimoto sheaves, and a lot of this has an analog in the finite flag variety case. So I want to do the finite flag variety case first because it's a little bit easier, and a lot of the proofs in the affine case are analogous. So now I want to start with a fun calculation. Which is the following. So I'll try and draw a nice picture of P1. Here's P1. And I want to take 2 points, 2 distinct points in P1. So we fix x is not equal to y. points on P1 of C. And what I want to do is, so we can consider the following diagram. We can take away these 2 points. And now we can put them back in. So the subscript denotes the point that we're putting back in. And I'll use a standard abusive notation by denoting different maps by the same symbol. Okay, so there's 2 ways that we can put these points back in, and there's a lovely little exercise, which is to show that, so basically what we're going to start is with the constant sheaf on the complement. And then we're going to put these 2 points in, but we're going to put one in with a shriek and one in with a star. So J, X shriek, J, Y star. And the exercise is to show that this is the same thing as doing it the other way around. Right. And just for the younger members of the audience, how do you prove such a thing? Well, you first use kind of general blah, blah, blah to argue that there's a map. And then you check that this map is an isomorphism. Okay, so that you'll use some kind of a junction to argue that this home space is Q. So you'll choose a map inside that space and then show that it's an isomorphism. And I want to denote this thing by Q, X shriek, Y star, this sheaf. Okay. So a picture of this sheaf up here is that it has stalk Q everywhere, and then except for at X and at Y, and at Y we extend it by a star, and at X we extend it by a shriek. Okay. So you can actually develop a whole calculus, which Carrie's explained to me in the past, where you imagine Riemann surfaces with shrieks and stars distributed around them, which is really... Okay, so the claim, this is the fun calculation, is that the cohomology on P1 of this sheaf X shriek Y star vanishes in all degrees. Okay, why? First, I want to give you a prosaic way of seeing this, and then I want to explain briefly 2 other ways of seeing it. So it might look kind of silly little calculation, but it actually is behind many interesting things. So if we take the constant sheaf, so if we take Q Y star, so this is just J Y star, the constant sheaf on P1 take away Y. We have a standard distinguished triangle, goes to IX lower star, IX upper star, QY star. And then here we have JX Y star. So what I'm denoting the...
Sorry, can I ask a question?
Of course.
Maybe you already said that, but maybe I missed it. So when you wrote those lower star and lower shriek, are these derived or the original?
Always derived.
Okay. Sorry.
So there was a question in the chat that I didn't see.
No, it's the
Okay,
same.
so same question. Okay, so here I'm denoting by IX the inclusion of X. So this triangle is a consequence of the fact that I have a functorial distinguished triangle Okay, so I'm just applying this distinguished triangle to this object that I'm calling QY star, and I'm getting a distinguished triangle. Okay. So now we have a long exact sequence of cohomology. Okay, you know what this says. So here's my cohomological degrees, 0. Okay, so we're taking global cohomology so we're taking applied to this distinguished triangle. So here we just get the cohomology of P1 without Y, so we get Q. So this is just the cohomology of affine space. Here we get the cohomology of a skyscraper sheaf. So note that X is not equal to Y. And so this is simply a skyscraper sheaf in degree 0. And this map is an isomorphism because restriction of global sections from a constant sheaf to a skyscraper is surjective in degree 0. Okay. And so that says this is 0, 0, 0. Which is what we wanted to show. Okay. So let me just briefly give 2 exercises. So I want to explain, as I was saying, this looks like just a funny little exercise, but there's actually kind of some rather interesting things going on here. So exercise is prove this another way as follows. So use Artin vanishing which we will see later today, but is basically the fact that, so the really lovely thing about this is that I can, because of this isomorphism, I can either interpret this as taking cohomology of a perverse sheaf or as taking compactly supported cohomology of a perverse sheaf. And one vanishes above 0 and one vanishes below 0. And so use Artin vanishing to show that H not equal to 0 of this X streak Y star is 0. And then compute that the Euler characteristic of this thing is 0 and conclude. Okay, so I have I first argue that the complex is concentrated in 1 degree, and then I use an Euler characteristic argument to show that it's 0. Okay. And why is this Euler characteristic 0? Basically, it's because the Euler characteristic of this is I've taken the Euler characteristic of P1 and then I've removed 2 points, both of Euler characteristic 1. And so I'm taking the Euler characteristic of P1, which is 2, and I'm taking away 1, and then I'm taking away 1, and I get 0. So exercise A. Exercise B. So this is very useful because it illustrates this general principle of using art and vanishing. Exercise B is just more for fun. Interpret that the cohomology of P1 with values in this sheaf as certain locally finite chains. So it's kind of, you can interpret this sheaf cohomology as some mix of Borel-Moore and normal homology and conclude immediately. Okay, so there's this beautiful book called How to Solve It by Rota, I think. Polya. And Polya says, when you've solved a problem, then you should solve it again and again and again until you can see the solution without thinking at all, or without any effort. And somehow, I think that this is a way of seeing this answer without any effort whatsoever. Okay, so this was a fun calculation.
Geordie, can I ask about exercise A?
Mm-hmm.
I think maybe the degree that you first showed that it's concentrated in is not 0, it should be 1 probably.
Yes, sorry. I'm thinking that maybe to match art and vanishing, we should say 0, and then we should
put the shift there. Yeah.
Thank you very much. Are there any further questions about this?
Maybe just to point out in your first proof, the one there with the long exact sequence, what you actually showed there vanished was the cohomology of something slightly different. The JX lower shriek, JX upper shriek, Q, you got to do some base change and stuff to show that that implies what you...
Yes, I mean, this is Q X shriek Y star. By 1 base change, maybe.
Yeah.
The other thing, another comment for students is that this lecture will have more exercises than normal, and please try to do them. Just a general comment, but yeah, I've said this before, but that we're reaching the point in the course where you cannot stay afloat without swimming. Okay, so finite Hecke category. So basically the rest of today's lecture will be about constructible sheaves on finite flag varieties. So GBT as usual. And for simplicity, we take it over C, and our coefficients are, for simplicity. Nothing that I'll do today actually needs this choice. And we work with So I try not to write the coefficients the whole time. And just a remark is that in lecture, no idea, something like it's in an epsilon neighborhood of lecture 32 or something. This is an approximation to the Hecke category. So everything we do below can be done in the proper Hecke category. It's just more difficult to explain, and so I'm explaining it in this setting to give ideas. And the fundamental structures. That we'll be using the whole time is we have the convolution. So I won't go over the definition of this convolution again. Maybe I'll stop writing. I'll simplify my life by not writing B's. Okay, so I've discussed this convolution a number of times. And a very important point that is probably has not been emphasized enough so far is we have two different incarnations which are really very it's very important to keep them separate in your head. So this means B constructible, and this means B equivariant. And here there's no convolution. And I think that in the early days of the subject, when people were first investigating these Hecke categories, if you look at the literature, there's quite a few wrong statements because this distinction is not clearly made. And inside here we have PB, and inside here we have PB, and so these are equivariant. Perverse sheets. Okay, and we also have the Bruchard decomposition. I'll try and keep writing WF for the finite file group to remind ourselves that we're really headed for the affine case. And the absolutely key players in this lecture will be JX Shriek of Q. So I denote by B the inclusion by JX. And so we saw, so just in order to notation, so apologies for changing notations between lectures, but I think it's really important. It kind of, each lecture has a slightly different goal. So I just want to employ the following notation, that if we take G mod B inside here, I want to denote by F dot the forgetful forget equivariance. And you can see that this is actually another way of getting this object, is just taking the unit, or taking the which is also known as well, taking this and convolving on the right by F. Okay, that's another way of saying what this F dot is. And remark absolutely no idea which lecture this was, that these sheaves, when we forget equivariance, give standard and co-standard objects in a highest weight structure. On this category of B constructible perverse sheaves. Be very careful, however, because one shouldn't expect the equivariant category to be highest weight. And in general, it is not. Are we going for time? Okay. Are there questions based on this general business? So I'm relying somewhat on previous lectures here. So if there's some notation or some concept that is annoying you, please let me know now, because that will probably continue to annoy you for the rest of the lecture.
So, Geordie, could you please remind us the relationship between P lower b and P lower bracket b?
So roughly speaking, Elijah, thanks for the question. I'll answer that in a second. So Masood is asking about the difference between PB and P brackets B. And so we have this.
You like to call both of them equivariant perverse sheaves?
No, one is, sorry, this equivariant refers to this thing refers to this side.
Ah, okay.
These are constructible perverse sheaves. And one way of thinking about this is that we have this, maybe I'll write this. So we have P, B, PB. So this is forget equivariance. And it's and this is fully faithful. But the image is not closed under extensions. Under extensions. Under extensions. So a very nice exercise, which follows on from some lunch discussions we've been having. So for G equals SL2, we have IC identity, ICS, and TS. This is so-called big projective or interesting tilting sheaf. So there's 5 indecomposable perverse sheaves. So this is in P constructible. In PB, all of these are constructed in some easy, IC sheaves always admit equivariant lifts. Standard and co-standard modules are defined. I mean, I should really write ... But there's no lift here. Okay, so you should think about this category as being basically the same as this category, except certain objects don't exist. And somehow these missing objects make this a much less nice category than this. So this is highest weight, etc. And there's about 7 different ways of thinking about this exercise. Very important exercise, and we'll definitely come back to this. And we've already seen it in previous exercises also. Does that clarify things, Masood?
Yes, thank you.
Okay, Elijah, do the delta generate the equivariant category still? Yes, they do. Basically the same argument that you might have seen, that the deltas generate the non-equivariant one, just works. And that's another exercise, which I won't write down. Okay, so now I want to get to the braid group. So we have this finite Weil group that admits a Coxeter presentation. Such that and of course the braid group is the same thing, except we drop the quadratic relation. Okay, I'm sure everyone here is familiar with braid groups by now. So I'll make the standard remark that in type A we get the classical Artin braid group. So we have the following important and beautiful theorem. This is very important for this whole world of geometric representation theory. And you can start World War III by asking at a Nobel Wolfach conference who this theorem is due to. So this map that sends a simple reflection to delta of S extends to a monoidal functor So from this is the monoidal category. Associated to the braid group. So it has objects indexed by elements of the braid group and no morphisms between different elements and only the identity morphisms, and then the monoidal structure is given by multiplication in the group. And if that was too fast, then look at lecture question mark. Lecture now -3, I guess. So we have a monoidal functor from this very simple braid group monoidal category to the Hecke category. So I want to explain how to prove this, but first a corollary. Of this is that this braid group acts strictly on dB G mod B. Okay, so this acts on dB G mod B, and so we can use this monoidal functor to get an action. And this is an action that's seen right throughout kind of highest weight theory as some kind of translation functors or shuffling functors, or there's many different names and many different incarnations of this. So we actually want to establish, we don't just want to establish a weak action, we want to establish a strict action. And there's a nice theorem of Deligne that allows us to do this, which is a good instance of this kind of generators and relations philosophy. So I want to go through this briefly. So proof use the following. Theorem of Deligne. So this is probably one of these papers that should be on our list of papers one should read sometime. This is called Axial d'une groupe de tresses. I can't remember the exact title. And basically what he says is that in order to give, giving a monoidal functor from this so is the same as, so remember that in order to give such a monoidal functor, in theory, we should give a functor for every single element of our braid group together with a whole lot of compatibility data. And then we discussed in several examples that sometimes this compatibility data can be boiled down to a much simpler set of things. And this is the boiling down that occurs in this case. So it's the same thing as giving an invertible element an isomorphism whenever the length of xy equals the length of x plus the length of y. And then, so remember in two-category language, this often has the like a three-layer structure. So we're given an object, a morphism plus a condition such that commutes and as is typical in such definitions, my handwriting slowly gets smaller and smaller as the conditions go up in higher categorical level. Okay, so how does one think about this theorem? If I just go back up briefly to the braid group, so I'll just go back up to the definition of the braid group up here. So we have a map, an obvious map here that sends sigma s to s, and this has a section which is called positive lift. And this is not a homomorphism. So this sends W to sigma S1, sigma SM for any reduced expression W equals S1 up to SM. So you can think about the braid group as having either been generated by simple reflections or as being generated by positive lifts of Weyl group elements. And what this theorem is saying is that these positive lifts of Weyl group elements provide a small enough skeleton on which to define this action. So these f of x's below are precisely the images of the positive lifts of the Weyl group. Okay. So what is kind of easy are these isomorphisms and this square, and what's a little bit more tricky is the invertibility. So I want to do the so most data follows from. So maybe I can copy lin 1 and make this small so that we know where we're going. So lemma if L of xy equals L of x plus L of y, then delta x convolved with delta y is isomorphic to delta xy canonically. So proof recall that delta x is jx lower shriek of constant sheaf on bx, b mod b with some shift. And if we unpack the definitions, we get that delta x convolved with delta y is m prime lower star of the constant sheaf on b xb times over b byb times over b. So what I'm saying here is we have bxb times over b by b b goes to somewhere. I mean, goes to G mod B. Sorry. And this goes into G times over B, G mod B. And what I'm saying is that this object here, when we unpack the definition of convolution, becomes the Schriek extension of the constant sheaf here under this map, and then we push it forward. But we can just we could just push it forward via Schriek along this map. This is M. Right. But if the length of xy equals the length of x plus the length of y, then it's a standard structure theory result in reductive groups that M prime is an isomorphism. ISO. So the following map is an isomorphism. Okay, this is, for example, this is an example of this phenomenon is describing the open Brouwer cell as a product of unipotent groups for simple reflections. That's what's going on here. So this thing, this is just the same thing as the constant sheaf. This is JXY Schriek of the constant sheaf on BXYB mod B, which is the same thing as delta XY. And we can rigidify this isomorphism by asking that it's the identity, for example, at the point XY. And so we get a canonical isomorphism. Okay, so that means that this lemma implies that we have this and we have this, and maybe let's have a break for 7 minutes and we'll discuss the invertibility.
Can I ask a stupid question about history?
Sure, but you're never allowed to say that a question is stupid.
Oh, okay, I'm stupid. Okay, is that allowed? No,
No.
never. Oh, so the theorem that you stated, where you said they argue about it in Oberwolfa.
Mm-hmm.
So I first saw this in the 1980s manuscript by Beilinson and Bernstein. Is there any earlier claim?
Well, somehow this idea of kind of braid groups acting on category O and stuff is to some extent in work of Joseph and Constant and
I see.
And so you can ask, to what extent did they phrase it as a braid group action, and to what extent were they aware of strictness and all those kind of things, and then you start an argument. But
oh no, okay, I was curious. I see. Very good. Then they are earlier.
And it's really, I mean, it's clear that people were simultaneously aware of this in different areas and things. So yeah,
Okay.
I think
That's good to know. Thank you very much. I have another comment, but maybe after tea.
Oh, sure. Or maybe you can make the comment and then we can digest it whilst drinking tea.
No, no, I was just going to say a small thing about your pictures. So Macpherson always liked to put a green dot to the stars and a red dot to the shrieks.
Uh-huh.
And the red dot means because he thinks in homology that you're not gonna allowed to go near it. And the green dot means that you can go into it. And this way of thinking is very useful, I think. Like this hyperbolic localization, you can see immediately if you think in terms of this green and in terms of cycle chains, if you think in terms of this green and red.
I just want to illustrate what Carrie's saying in a picture. So when we're thinking in homology, we're thinking about green cycles that can disappear into the, cycles that can disappear into the green areas, but they're not allowed to go into red. Okay. And so you're saying that hyperbolic localization, okay, I need to digest why hyperbolic localization is really nice from this point of view.
The shriek and the star upper shriek and upper star restriction kind of commutes this way. That's usually called nowadays called Braden's theorem.
Mm-hmm.
That was a long time ago in these Macpherson and Gorsky-Macpherson pictures. Just pointing out that if you want to think in terms of cycles like this, it can sometimes be useful because then you discover these theorems easier maybe then.
Mm-hmm.
Maybe the hyperbolic thing wasn't so easy to discover if you think in terms of shrieks and stars, unless you are very clever with shrieks and stars. But if you think in terms of these geometric pictures, you'll see it. Now, if I could remember now why it's immediately obvious, I would tell you, but I can't remember at the moment.
I do remember your explanation in Oberwolfach that was very useful.
You mean like 13 years ago?
Mm-hmm.
Oh.
Let's maybe really digest and have some tea and Okay, let's begin again. So remains to show that the delta x are invertible. And we've just seen that delta x can be realized as such a convolution. And so hence that delta s for a simple reflection is invertible. And now we have lemma 2. I might have forgotten to mention it, but the previous lemma was lemma 1. That the inverse of delta s is nabla s. And a remark that I won't write down is that there's several ways of seeing this, but I don't think any of them is purely formal. I don't know a way of seeing this without doing something at some point. I want to give two proofs, and both of them I'll only sketch. So proof sketch 1, I would say would be the more hygienic, but maybe less interesting. So in both proofs, we first reduce to SL2. Okay, so we can assume that our group is SL2. And now we have a distinguished triangle. Of perverse sheaves, which is that nabla s has IC s, which is Q P1 as a sub, and as a quotient it has IC of identity, which is Q in 1b. So this is an exact sequence of equivariant perverse sheaves. In other words, it's a distinguished triangle in the ambient category. And now we use that this preserves distinguished triangles. So we get and remember that this is the monodal unit, so we get simply delta S here. So this means that we get a distinguished triangle like this. And now I don't want to ruin the surprise. So I will partially ruin the surprise by saying that this is isomorphic to Q P1. And so if we put this over the other end of our distinguished triangle, this becomes IC S. And we argue that this is non-zero. And if this is a non-zero map, then we know that there's a surjection from delta S onto ICS, whose kernel is precisely IC of the identity. So this means that delta S involved in nabla S is the kernel of this map, which is IC of the ad, which is the unit. Okay, so exercise. Give the details here. And I'm running a bit slower than I thought, but I wanted to give a less hygienic proof, which I like better. Sorry, did that go too fast for anyone? Okay, so less hygienic proof, proof sketch 2. So SL2 times over B, SL2 mod B is isomorphic, as we've seen a number of times. So G prime B, it's isomorphic to P1 times P1 under the map that sends first project or multiply and project. And under this map, B times over B, SL2B goes to, so I want to draw a picture of this. Where, so this is P1 times P1. And this is the second factor. And this is the first factor. And then under this isomorphism, the convolution map just becomes the projection. Okay, these convolution maps you can always rewrite so that one of the maps just like the map that you're pushing forward to under just becomes the projection. Under this map, this piece here goes to the x-axis. So this is base point times P1, and SL2 times B over SL over B mod B goes to the diagonal. And I'm going to suggestively, following Carrie's comment, denote this by green and this by red. So this is the diagonal, and this green axis I want to call Z. And now again, unpacking, we see that the non-equivariant sheaf underlying. So basically, if we take this convolution and then forget that it's equivariant, then this is, let's call this P lower star of the following thing. We basically do a star extension along here and tensor with a shriek extension along here. this P lower star of J delta star of Q P1 times P1 without the diagonal times JZ shriek of Q P1 times P1 without Z. Now, what's really beautiful here is that we can compute of this via proper base change theorem. Oh, and there's a shift. Two, which is, please tell me if there's any more typos, via proper base change theorem. Okay, so we have this sheaf here, which is a tensor product of a star extension along here and a shriek extension along here. And we're taking this sheaf, we're pushing forward under the projection, and we want to know the stalks of this. So the stalk here will just be the cohomology of the restriction of this sheaf to the fiber. So the stalk at some point X in P1 is the cohomology of P1 with values in this thing that has a, with what I was calling at the very beginning, 0 shriek X star. It's not equal to 0. And it's the cohomology with values in the extension by 0, 0. So J0 shriek of Q. If X equals 0. Okay. So this sheaf looks like one of these star shrieks away from 0, and at 0 we just get an extension by 0. Okay, and now by the fun calculation, this is 0, CF fun calculation, and this is just Q. Okay. And now there's an extra argument which you can make, which is that if you know that the underlying equivariant sheaf is a skyscraper, then the equivariant sheaf is a skyscraper too. The reason that I like this argument a little bit better than the other one's kind of more formal, but this one shows to some extent geometrically what's going on. Are there questions based on this calculation? Okay. So again, fill in the details if you would like to. So now I just want to discuss briefly HOMs between the deltas and the nablas. of image of braid group. The first very important property is that hom dot delta x nabla, sorry, we have y is 0 unless x is bigger than y. Hom between the nablas. Unless x is smaller than y. And hom dot so there's no homs from a delta to a nabla unless you're in degree 0 and, oh no, so this is wrong. Sorry, this is correct in the non-equivariant case, but it's not correct in the equivariant case. So I'll just say that hom delta x from nabla y is 0 if x is not equal to y. So the way to picture this, I mean, one way to picture it is we have simple reflections and then we have STS. And this is saying that the nabla maps only go up in Breuer order. So this is the nablas. And the deltas only go down. Okay, and I'll leave, because I'm running a little bit short on time, I'll leave the proof of that, which is the simple instance of using adjunction morphisms. And just one remark is that in BWF, hom spaces are easy. In the image of the braid group inside the Hecke category. So just an example is X groups between Verma modules is unknown. And apparently very difficult. Okay, so in this category, we have very simple hom spaces. But this is an example of something that I've discussed a number of times where in kind of categorical representation theory, we often want to add maps, non-invertible maps even between group elements, and that these maps take on a high degree of significance. And we've seen a little bit of that in the last lecture with these maps between these conditions for things to lift to some kind of actions of coherent sheaves in Bezrukavnikov's work. Okay, so I would dream at some point of having some good understanding of the homomorphism spaces in the image, but we don't have such an understanding at the moment. I want to finish with a really beautiful observation of Merkovich, which motivates a statement in the more general setting. So in the affine setting next time. So we have D And recall that this is highest weight with simples ICX, standard modules, co-standard modules. And for us, these are very important role will be played by the tilting perversities. Now, definition. So we've made a number of times, we've made a big song and dance of the fact that if I convolve two things in the Satake category, I get an actual perverse sheaf. And we've seen in general, for example, if I convolve the constant sheaf on G mod B with itself, then I get basically the cohomology of G mod B times that constant sheaf again. And so it's scattered throughout a whole lot of degrees. And so one way of understanding that is that there's kind of, we can't hope for any exactness with respect to perverse T structures of this action. So if I take a perverse sheaf here and take a perverse sheaf here and act, then there's no reason to expect it to be a perverse sheaf anymore. But sheaves that satisfy this play a very important property. So play a very important role. So if we take inside here, inside PB, so this is the constructible perverse sheaves, and here we have ordinary perverse sheaves. So we say it's convolution exact if we act on by any is in PB, for any G in any equivariant perverse sheaf. And an exercise for later, just to give you a feeling for the kind of why the following statement is rather remarkable, is that we can also formulate what it means to be convolution exact here. So F if and only if is a direct sum of the unit. Okay, so the unit is obviously convolution exact, and that's the only equivariant sheaf up to taking sums. It's convolution exact here. But we have the following observation of Merkovich. So it's very beautiful. It says that F inside PB is convolution exact if and only if F is, does anyone want to guess the answer? So it's nice to go. So here, so this is convolution exact. And then the exercise for later is to rule out that none of these are convolution exact. And there's only one possibility left, which is this big projective. And it turns out that this is convolution exact, or the tilting. So Merkovich's observation is that this is convolution exact if and only if F is tilting. Okay. So very beautiful statement.
But
So now,
do you know, I mean, here you always deal with somehow this B constructible from the left.
mm-hmm.
So you of course don't have to, you can just act on the whole thing, on the whole derived category.
Yes.
So are there other, so what would the other, are there then other objects that would be convolution exact?
So definitely. I mean, yeah, I can produce silly examples by just moving convolution exact things around by G and stuff like that. But
Yes.
It's an extremely good question if there's any more.
Exercise.
Exercise, very good question. I didn't think of this question when I was preparing this. So let's prove Merkovich's observation. I first want to prove this direction. So if it's convolution exact, this is somehow the tricky direction, because the other direction we know a lot about tilting, so you can kind of check it directly. Whereas this direction we actually need an idea. And so highest weight blah blah blah. Tells us that F is tilting. So the definition of tilting involves it has a filtration and another filtration, but there's a homological criteria, namely that the X, hom bigger than 0 from F to nablas is 0 is hom bigger than 0 from deltas to F. So I'll call this condition star and this condition shriek. So like one direction of this is obvious. If I have a standard filtration of this, then by the long exact sequence, this hom space is 0. And similarly here for a co-standard filtration. And then the beautiful thing that happens in highest weight categories is that this is if and only if. So we check shriek, and star is similar. So F is convolution exact, implies that F convolve with the longest element is perverse, which implies that F convolve with the longest element is in PD less than or equal to 0, which in a close variant of Elijah's question, you can see rather easily is generated by the positive shifts of standard modules. So, I mean, I always think about this wing of the T structure as being given by something to do with stalks, and the other wing is given by something to do with co-stalks. And these are the things that have easy stalks. So this is for all y in W and F and D in Z. Bigger or equal to 0. So now this tells us that F is in, we can undo this operation. So F is I should have said before, but the inverse of delta, because the inverse of delta S is nabla S, the inverse of delta X is nabla X inverse. So this D or Y in WF and D in Z bigger or equal to 0. So this implies that F is in. So now there's another beautiful property of the longest element, which is that I can always write, I can extend any element to an element, to the longest element in an additive way. And so I wrote del, so probably I've got this slightly wrong. So what's this equal to? Oh no, I think it's right. Okay, and now if you have an object inside this category, then it's easy to see that it satisfies shrink. Okay, so that concludes this direction. So this seems to me like a typically Merkovich style proof. Maybe we can call it a Merkovichian proof. So now we need to go the other way, and the other way will be useful for other reasons. So I'll cover that briefly and then we'll be done for today. I'm moving on in, unless there's questions. So we need, for the other direction, we need the following theorem. And this is a rather deep property, I would say, that it's kind of deep, but you use it so often that you think it's obvious. If we have an affine morphism, then F lower star preserves P D less than 0, and F lower shriek preserves P D bigger than or equal to 0. Okay, so this is kind of the cohomological dimension of affine morphisms. It's very important. And how on earth do you not forget this? So recall art and vanishing. So this was promised at the very beginning of the lecture that this would be covered, which says that if f on x is perverse, then the cohomology of x with coefficients in f is 0 above degree 0. Remember that we expect for a perverse sheaf the mirror of Poincare duality to be the middle degree, to be 0. And so normally for projective variety, we expect it to be distributed above and below 0. But for an affine variety, we expect the cohomology to stop exactly at 0. And similarly, we expect the compactly supported cohomology. And of course, this is just if f is the map to a point, this is just the cohomology of f lower star of f. And this is the cohomology of f lower shriek of f. And so this is in PD bigger than or equal to 0. So the perverse T structure on a point is simply the standard T structure. So the moral is that Artin vanishing is this theorem for so Artin vanishing is a consequence of theorem for y equals a point. And just an exercise. So you might also know that affine morphisms have good exactness properties for coherent sheaves or quasi-coherent sheaves. So the exercise is to decide what does the theorem mean for D modules. Or if you allow yourself the Riemann-Hilbert correspondence, can you reprove the theorem via D modules? So back to our setting, if there's no questions on this slide. So basically where we want to go now is that convolving with a delta x or convolving with a nabla x is given by a star or a shriek along an affine morphism and therefore satisfies exactness properties. So proposition that the restriction of the convolution map, so bxb times I'm going to call this lambda x so the restriction of the convolution map to a single Bruja cell are affine. Why? So remember that we can write bxb to be ux times some representative of x times b. So if we look at lambda x, if we look at here the multiplication, we can, this is isomorphic to ux times g. And so this is unipotent. This is a unipotent subgroup. And the point is that this is affine. So this implies that mult is affine. And that implies that lambda x is affine. So I'm sure there's many different ways of proving this. So the way that I convinced myself this was true was because flatness is, kind of being affine is local in the flat topology. Another way of saying this is if I have an affine map and I take a free quotient of this affine map, then it stays affine. Okay, so these are maps, and now another exercise is that convolving on the left with delta you can write this functor as simply being lambda x lower shriek of lambda x upper star shifted by the length of x. And similarly, okay, so these operations of convolving with one of these deltas or nablas can be expressed simply as essentially as a push forward. So for nablas, this is a proper push forward, and for nablas, this is a push forward, and for deltas, this is a proper push forward. And just in order to do this exercise, it might be important to note that lambda x upper shriek is lambda x upper star twisted by twice the length of x because it's smooth of relative dimension. Okay, so a corollary is that convolving on the left or convolving on the right with deltas preserves PD bigger than or equal to 0 whenever this makes sense. And similarly, convolving on the left with the nabla or convolving on the right with the nabla preserves and now we have enough. So one important corollary that will be important next time useful next time. So it probably seems a bit random at this point, is that if I take any convolution of a delta and a nabla, it's kind of surprising, these are always perverse. I have to stop at one convolution. I remember being very mystified by this at some point in a different context, in a context of Zogel bimodules. But in this setting, it's rather, I think it's rather transparent. Okay, because, I mean, why is this true? Because I can interpret it this in two ways, both as action on the left on something perverse, or as action on the right on something perverse. And in each of these interpretations, one I get this inclusion and one I get this inclusion. It's maybe a tiny little bit subtle. Okay, so now I can prove the other direction of Merkovich's observation. So of observation. So I just realized that what I said we would need next week we actually need right now. So this wing of the T structure is precisely generated by all of these guys, and it's like this. And now we apply the corollary to deduce that any so if I consider the full subcategory generated by nablas, and I act by PD less than or equal to B. So this is the thing that I've just described over here. Okay, and so now we use the corollary to say that this is in PD less than or equal to 0. So a tilting belongs to here. So this says that a tilting is perverse. And similarly, sorry, not is perverse, but is in this wing of the T structure. Similarly, tilting convolve with PD so this implies that tilting convolves with an equivariant perverse sheaf belongs to here. Now, so I want to finish with two exercises. A, the earlier exercise. So now you can actually do the earlier exercise. So F in PB convolution exact implies that F is a direct sum of the unit. And just a remark is that next week so the reason this kind of negative result is interesting is that in the affine case, it becomes totally false. So we'll see that there are many convolution exact F inside affine flag pattern. And B, I feel like I would be cheating a little bit if I didn't mention the following fact, which is that suppose Tx is indecomposable tilting, show that Tx convolved with one of the generators of the Hecke category is 0 unless X is the identity. So related is the fact that the cohomology on G mod B of Tx is 0 unless X is the eigenity. And so whereas before it looked like there was some kind of magical thing that's keeping all of these Tx's perverse, they're usually not perverse in a particularly, like, the reason that the convolution with something in the Hecke category just often gives 0. That's all I'm saying. And use star to reprove the direction that we just checked. Observation. Okay, that's all for today.